Good evening and welcome to York Festival of Ideas and this session on space exploration and technology, Earth observation and science diplomacy. My name is Maria Berdahl. I work in the European Commission as a program officer for Copernicus, the Earth observation component of the EU space program, and I will be chairing the event today. It's my great pleasure to welcome you all here this evening. Now, before our panel, I would like to welcome Dr. Patrick Nedelec, Science and Technology Counselor at the French Embassy in the UK. Patrick, the floor is yours.
Thank you very much, Maria. It is really a great pleasure to welcome you all to this panel discussion talking about space exploration to understanding Earth, taking place today at the International Space before the International Space Summit to be held in France in September. So for us, it's very important to organize such events with the York Festival of Ideas. We are very honored to have with us today such an outstanding French and British experts from various and prestigious institutions, the European Space Agency, the UK Space Agency, University of Leicester, University College London, and the European Commission, as Maria, you represent today. And your insight and experience will be very important for this conversation. I would like also to warmly thank all the participants, Maria, Suzie, Clement, Jean-Christophe, and Matthew for their participation. This exceptional panel is the result of the fruitful collaboration between the Higher Education and Research and Innovation Department from the French Embassy in the United Kingdom and the York Festival of Ideas. I would like to really express my heartfelt thanks to the organizer of this fantastic festival, and especially Sarah Mitchell for her dedication and full commitment and the French Embassy has been collaborating with the York Festival of Ideas for more than 10 years now, and we are very, very happy of this partnership that will foster exchanges between British and French researchers. Today's panel discussion is taking place 2 weeks after the second Franco-British dialogue on science, technology, and innovation, offers a timely opportunity to celebrate the strong bilateral cooperation in space, which contributes significantly to joint governmental priorities such as scientific cooperation in emerging technologies, addressing global climate, environmental crisis, disaster response, ocean protection, global health issue, and fostering business, commercial, and industrial ties. This cooperation in space is reflected actually in several flagship projects. Let me give you just some examples, three really fast examples. The first one is a cooperation between CNES and UK Space Agency on the mission called Microcarb, dedicated to monitoring the carbon emissions, very important issue indeed. The second one is the SWOT mission that is developed by NASA and CNES with the contribution of the UK Space Agency, which aim is to transform and understand the global water resources in our planet. Again, indeed, a very important issue. And the last one is the next generation atmospheric sounding instruments that has been developed through cooperation between France, the United Kingdom, and leading European industrial partners. I would like also to highlight our shared participation in the European Earth Observatory program Copernicus, as Maria already mentioned, which remains one of the world's most ambitious and successful space initiatives. At the time when geopolitical tensions are increasing and when global challenges require collective response, strengthening European scientific cooperation is one of the core priorities of our departments here at the French Embassy in the United Kingdom. And this evening discussion fully reflects that ambition by bringing together leading voices from across Europe to explore how space exploration and Earth observation can help us better understand and protect our planet. Thank you very much for your attention, and I wish you all an enjoyable evening and a stimulating discussion. And I give you back the floor to you, Maria. Thank you very much.
Thanks a lot. Thanks a lot for those words, Patrick. So now we will move on to our panel discussion, and our first speaker tonight is Clement Albergel, who leads the European Space Agency's work on actionable climate information, translating satellite data into information that drives global policy. His team oversees the Climate Change Initiative, which produces gold standard data sets such as ice sheet melt, sea level rise, and greenhouse gas concentrations used by the IPCC, the COP negotiations, and national governments. So in his talk, Clement will highlight the role of space agencies when it comes to monitoring our environment. So the floor is yours, Clement.
Thank you very, very much. So thank you very much for this very nice introduction and for having me. I work at EXAD, home of the European Space Agency in the UK, although tonight I'm calling you from beautiful Paris. When we talk about environment, we say that we are going through a triple crisis: climate change, biodiversity loss, and the issue of pollution. It's only with a coordinated effort that we will be able to address those crises. Climate change is arguably the greatest environmental challenge facing us in the 21st century. And with worsening impact predicted for generations to come, climate change should be high on economic, strategic, and political agendas worldwide. There is some work to do, but I'm sure that the international community can work together to stabilize the evolution of our future climate. But to take decisions on how to adapt to climate change, how to mitigate the impact of our changing climate, the international community requires systematic observation of the climate system to observe, to understand. And that puts the role of space agencies, of the European Space Agency and its member states, in the spotlight when it comes to climate and climate action. Satellite Earth observation has a unique capability of observing the Earth everywhere, all the time, providing continuity in the measurement. At ESA, we've been dedicated to observing the Earth ever since the launch of our first weather satellite back in the 70s. And on this slide, you have all the missions we have prepared or are preparing in our three main lines of activities: pure science with the Earth Explorer, making sure that Europe stay at the top; meteorology, operational satellite used every day for weather forecast; and in the middle, between science and operation, you've heard about it already, the Copernicus program of the European Union and its dedicated fleet of satellites, the Sentinel. It is the biggest provider of satellite data Earth observation in the world that follow a completely free data policy. Now, how do we go from those data to climate? As a direct response to the need from the international community for systematic observation of the climate system, ESA has developed its Climate Change Initiative in 2010. It is a research and development program that we coordinate together with our member state, and that main objective is to develop global scale, long-term, satellite-derived time series of key components of the climate system, also known as essential climate variable. The climate quality data sets that we produced are a major contribution to the evidence-based used to understand climate change and hopefully drive international action. The essential climate variables are all around us. It can be sea level rise, greenhouse gas concentration in the atmosphere, land cover change, soil moisture, forest, above ground biomass. This slide illustrates our activity in my team. If you start at the bottom left, we develop satellite-derived climate data record so we can assess the state of the climate and we know where we stand. We work with the modeling community to improve climate projection scenarios so we know where we are heading to and can provide early warning of changes, and most pressing, the transparent information, unrestricted by borders, needed to track the collective progress made towards achieving the main goal of the Paris Agreement for climate. We provide the crucial line of evidence for informed decision making. This is an example. We can monitor since the late 70s the extent of sea ice in the Arctic. And you can see that it has been going down. Here we have a view in 1979, in the summer months, and more recently. And climate prediction, informed by satellite data, show that the Arctic Ocean is likely to experience ice-free summer before 2050. From space, we can also measure land surface temperature. It's not air temperature to the meteorological sense, but rather the amount of energy that radiates from the surface. And it's usually warmer than air temperature. Think about when you go to the beach or walk on the road in summer, it feels very, very hot. And because we have developed long-term data set of land surface temperature, we can put today's measurement in perspective. Yes, it's getting warmer. Over to you, Maya.
Thank you. Thanks a lot, Clement. We will get back to this topic in our Q&A session. But for now, we will move on to the next speaker. It's Matthew Cook. He's the head of space exploration at the UK Space Agency, where he oversees the UK's ESA portfolio, ensuring British expertise included in European space missions. Before joining the UKSA, he was the UK's Air Protection Science Advisor at the Ministry of Defence, where he revolutionized how we shield aircraft from hostile threats, earning a Vice Chief of Defence Staff commendation for his works. So Matt will address the benefits that space exploration has brought to us, including the scientific advantages and advances which have been made to facilitate space travel and how those are being used to improve our everyday life.
Thank you, Maria. Much appreciated. And good evening, everyone. It's an honor and a privilege to be with you as head of space exploration at the UK Space Agency. My remit covers astronauts, the moon and Mars. It's an incredibly lucky job that I find myself in, for sure. But when we hear space exploration, when people hear space exploration, it sometimes sounds like the opposite of looking after Earth. But I'd argue the opposite is true. This picture behind me, hopefully you can see it well, is from December 1968. And to put this picture into perspective, everyone who ever was or ever will be is in this picture, except the crew of Apollo 8, Frank Borman, Jim Lovell, and Bill Anders. Space exploration is the only human endeavor that allows us to physically turn around and look at our world in its entirety. And in doing so, it helps us understand how to protect it, of course. At its core, exploration is about going into environments that are more extreme, more uncertain, and more fragile than our own. And space is the most extreme environment that we know, of course. If we can build systems that work reliably there, then those systems and the knowledge behind them often help us deal with challenges down here on Earth. So the value of space exploration isn't just about where we go, it's about what we learn, it's about what we build and what we bring back, crucially. And so I'd summarize that value in three ways, really. Exploration helps us understand the Earth better, it helps us solve problems on Earth, and it helps us work together on Earth's future. So that first point, exploration changes how we understand the Earth. When we study other planets or the space environment in general, we're really studying how planetary systems behave over time. For example, missions to Mars help us understand how a planet that once had water became inhospitable, which raises important questions about how climate evolves and what makes Earth stable at the moment. And closer to home, astronauts on the International Space Station have taken millions of images of Earth, helping scientists track storms, wildfires, and environmental change, of course. So space exploration gives us that perspective. But it reminds us that Earth is not just somewhere we live, it's a complex dynamic system that we're actively shaping. That second point about problem solving problems on Earth, space exploration forces us to solve very hard problems, and those solutions often translate directly back to Earth. Let me give you a couple of examples. So on the International Space Station for over 25 years now, it's been an orbiting laboratory where we can study biology in microgravity. That environment lets us observe things that are hard to isolate on Earth, how bones weaken as we get old, how muscles degrade, and how cells behave at the biological level. Those effects mimic many aspects of aging and disease, allowing us to test treatments faster and develop new approaches in healthcare. It's also been used to research things like drug development and vaccine research and new medical technologies, of course. Just recently, Artemis 2 sent astronauts around the moon for the first time in over half a century. And on the surface, that sounds like a political, geopolitical political mission. It's very symbolic, but its real purpose was practical. It tested life support systems, navigation in deep space, communication over hundreds of thousands of miles, and how we keep crews safe far beyond Earth orbit when we're in these extreme environments. These aren't just space challenges. They're challenges about resilience, autonomy, and operating in extreme environments, capabilities that matter for critical systems here on Earth too. And over the decades, the need to solve problems for human spaceflight has created technologies we now take for granted. So one of my favorite examples is the memory foam that we find in our mattresses was originally developed to improve astronaut safety during launch. Advanced camera sensors are now used in smartphones and medical imaging, and scratch-resistant materials like the ones that we find in our glasses were originally designed for astronaut visors on their spacesuits. In fact, there's thousands of technologies have transitioned over from space programs into everyday life. So when we talk about exploration, we're also talking about a pipeline of innovation for things down here on Earth. So I'll talk about the final value point for just a moment. The final, what do we get from space exploration? It's really about collaboration. Space exploration is inherently international. The International Space Station itself is a partnership between nations that have been working together continuously for nearly 3 decades now, since the intergovernmental agreement was signed back in the late 90s. And missions like Artemis 2 include contributions not just from the US, but across North America, Europe, and beyond. The European Service Module, for example, provides power and life support systems to the Orion capsule. And that matters because many of the biggest challenges that we face on Earth, climate, security, sustainability, are all also global. So exploration gives us a practical way of learning how to collaborate at scale, share systems from across different nations, manage those complex long-term challenges together. And therefore, space exploration really lights a beacon of hope in the darkness of space, making us humans ask the question, if we can do this, then what else can we do when we work together on this sort of thing? So I'll finish where I started. And space exploration is sometimes seen as looking away from Earth, but actually, as I've covered, it's one of the ways we can look back more clearly through missions like the Space Shuttle, the International Space Station, and now the Artemis program. We see a consistent pattern where we explore challenging environments, we develop new capabilities, and those capabilities come back to benefit society. So we're not exploring space to escape Earth, we're exploring space to understand Earth and how to take better care of it. Thank you, Maria, back to you.
Thanks a lot, Matt. Important points. And on the last one, on collaboration, just to mention, the ISS has been nominated several times for the Nobel Peace Prize. Even so, this really underlines the importance of partnerships and collaborations in space. So, moving on to our next topic and our next speaker. So, Suzie Imber is professor in space weather, the study of how solar winds and storms interact with planets, including our Earth. So she researches how these cosmic weather systems can disrupt satellites, power grids, and even airplanes. And it's a growing threat as we rely more on space tech more and more. So Suzie will address the interaction of the solar wind on the planets in our solar system and why this is important for us here on Earth. So, Suzie, over to you.
Again, just to reiterate, it's a great pleasure to be here with you today. So thank you very much for inviting me to give a little introduction to space weather with you. They were lovely first introductions to why we explore space and the climate and its environment. So thank you to the earlier speakers. That was brilliant. And I'm going to zoom in a little bit on a specific subject, which really kind of brings to life how space can impact life on Earth. So I want to just describe space weather, what causes it, and then I'll talk a bit about why it's so important to understand a little bit more, and maybe a little bit later we can talk about where the gaps are in our knowledge and where we need to get to be able to forecast this sort of space weather events. So I'm going to start with a little video. Here is the sun. This is a NASA visualization, and the solar wind is coming off the sun all the time, and it's taking about 2 or 3 days to reach the Earth, which is there in the middle, which is a magnetized body, and the magnetic field lines are in blue. And you can see they're kind of moving around. So the solar wind is giving energy to the Earth's magnetic field, transferring energy and momentum, and the field is changing, as you can see, and the energy builds up and up and up in the Earth's field, gets explosively released. Particles are attached to field lines, fly down them, hit the atmosphere, and they make it glow. And this is a cycle that happens all the time at the Earth. Now, as I said, a few times a day, we see this. And this beautiful aurora that you can see in my kind of background screensaver here behind me is the result of this. So energy momentum coming from the sun, entering the Earth's environment, energy being built up and up and up until it's explosively released, particles hitting the atmosphere and making it glow. So we see this beautiful aurora, 2 kind of rings of light in the sky centered on the magnetic pole, aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. And this is fairly routine. The thing that we worry about is not this sort of standard interaction I've just described to you. It's the extreme events that happen. And so in this cartoon here, very definitely not to scale, you can see the sun on the left and you can see the Earth on the right. Again, the magnetic field is given in blue here of the Earth, like a shield protecting us from the sun. But every so often we get these explosions on the solar surface, and that's what this cartoon is trying to show. So a bit of the solar surface is going to explode outwards and travel at speed through the solar system. If the Earth is in its way, then it's going to smack into the Earth's magnetic field, and big events hitting the Earth we call space weather events. So this thing that's exploding off the sun is particles and magnetic field coming out from the sun, kind of expanding as it comes out from the sun, taking less than a day probably to reach us. And these are the unusual events that we really want to understand, because these are the damaging ones. And they vary over what we call the solar cycle. So they're not happening randomly sort of across time, but they're clustered in time. So this is an image of the sun, just a representative image taken in a specific wavelength once every year. This is a bit of an old cartoon now, but you can see kind of in the 90s, mid-90s, sun was pretty quiet, not doing an awful lot. And as we go round to solar maximum in 2001, you see the sun is very active in this image. Seems to be quite a lot going on the surface. And then the sun gets pretty quiet again. And the solar cycle in total is about 11 years long. And we see many more of these really extreme events clustered towards that maximum in solar activity. And that's really helpful because it helps us to understand when we might expect to see these solar storms. It's not a predictor. They can happen at any point, and they do in the solar cycle, but more of them are seen towards solar maximum and perhaps slightly afterwards in the declining phase of the solar cycle. And we can map the sun's activity by counting its sunspots. So these are sort of groups of blobs on the solar surface. They've been counted for hundreds of years, and we can plot how many we see with time, and that's what you can see here. So you can see at the bottom there, we've been plotting this data since about 1750, actually a bit earlier than that. I wouldn't say those early observations were the most accurate, but over the last couple of centuries, we've got increasing accuracy here, and you can see the number of sunspots is going up and down, and that's the 11-year cycle I was talking about. What you should note, though, is that not every cycle is the same. So some of them are much more active at their peak than others. You can see that first cycle in that top plot there is pretty intense, quite active. Some of them have double peaked maxima. Some of them have just much lower maxima. Some of them have a more prolonged minimum. So the solar cycle is changing with time. We don't really understand exactly how the sun cycle is evolving. And we're at solar max right now. So 2025, 2026 is the maximum of this particular cycle, solar cycle 25. And you've probably noticed we've seen loads more aurora recently. You know, anyone watching in the UK over the last few years has probably seen aurora above their heads. This is unusual, doesn't happen very often per solar cycle. That's just an indication that we're in a particularly active time. Just to wrap up then, why should we care about this? Well, this cartoon kind of gives us some impacts on the Earth. So when we have big events that come from the sun, then different types of activity can affect us in different ways over different timescales. So we have X-rays given off, and they take 8 minutes to reach us. And then we have some highly energetic particles given off. They take a few tens of minutes to reach us. These are called solar energetic particles. They come at a fraction of the speed of light, so they're pretty quick and they're very energetic. We see coronal mass ejections. They take longer to reach us, maybe a day, maybe up to 2 days, but they are the things that I worry about. They contain a lot of energy and magnetic field. Although they travel slowly, they have a really big impact. They cause the big solar storms that we worry about. And okay, let's have a look at the right-hand side. They can do things like cause disturbances to the Earth's magnetic field, changes in the radiation belt, which are these sort of trapped particles that orbit the Earth, changes to our ionosphere and our thermosphere, so changes above our heads as well to the composition, density, etc. of this environment, and beautiful auroras. And the auroras are the kind of visible thing that we all enjoy about space weather events. But there are some downsides as well. Things like issues with communication systems, power grids, damage to power grids. This damage to power grids can be very widespread. You know, it could be most of Europe that have damage to power grids at once. It could be, you know, most of North America. So it's not like it's isolated to a little small area or even a single country. It's quite widespread. And so we have to worry about that with our interconnected power grids, you know, what happens if we have issues. Airline flights, I think Maria mentioned earlier, anything flying over the pole has to be redirected to lower latitudes. We need to have good communication systems with our planes, and that means they can't be flying over the poles where we see the most impact. Satellites can come crashing back down again. So we have to worry about satellites and their orbits. And whether increased atmospheric drag starts to bring down satellites and whether we have any fuel to boost them back again, or whether we end up with satellites coming down and burning up in the atmosphere. Malfunction of instrumentation, of course, we worry about that. And astronauts getting a high dose of radiation. So there's quite a lot of reasons why we should worry. But to put it into context, the biggest space weather events that we know of in sort of the last few centuries happened in the 1850s, and it was called the Carrington event. And in the 1850s, some telegraph operators got electric shocks in their ears. There were some small fires because we had currents flowing down telegraph lines and causing fires. That was the extent of it. And that was a really, really, really extreme event. But back in 1850, we didn't rely on technology the way we do today. And so the impact was not that severe, although being aware of the impact that happened helps us to understand just exactly how extreme that event was. If that happened today, there have been various forecasts around the impact, and I've described some of the things that could happen. And as we head into the future and we depend more and more upon these electronic systems, our satellites, for example, we have humans exploring space, as Matthew was talking about earlier so eloquently, we need to worry about their health. If they're out in the solar wind or on the lunar surface for any length of time, we have to worry about the damage to the health for these events. We are looking to a future where we rely on GPS systems more and more. You know, even just things like last summer, there was a space weather event, and in the US, it was crop planting season. Most of the crops are planted by tractors who are guided by GPS, and that couldn't happen. The GPS inaccuracy got up to something like 80 feet or something. Maybe it was 80 meters, sufficiently far that you couldn't rely on your tractors to be planting your crops. Crop planting was delayed and hundreds of millions of pounds was lost to the economy as a result. And that was a very minor space weather event, just as a really inconvenient time. So you can imagine that a big space weather event, which knocked out power grids and communication systems and airlines and all sorts, would be really serious. But as I said, they're pretty rare. So one of our really big challenges as space weather forecasters is how we can take an event that happens so rarely and try to unpick what the effect would be on society and technology today. But it's certainly something, especially at the moment when we have solar maximum and there's lots of events going on, that's beginning to enter the consciousness of governments and of society more broadly, something that we should have in the back of our minds, because even if the probability is rare that an event will happen, the probability is low, the impact is high. So I think I'll leave it there, and thank you very much, Maria.
Thanks a lot, Suzie. Absolutely an important topic that is not that well known also. So thanks for this this presentation. So moving on to the last speaker of this session, Jean-Christophe Mauduit. He's an expert in science diplomacy, a field that's never been more crucial as space becomes a domain of competition and collaboration. At UCL, he explores how science can bridge geopolitical divides, whether it's through space treaties, joint missions, or capacity building in emerging space nations. So in his talk, JC will explore these topics through a science diplomacy lens, moving from Earth observation satellites to space exploration and asking what cooperation might look like in an era of renewed rivalry. So, JC, over to you.
Thank you, Maria, and good evening, everyone. And it's been a pleasure to hear the amazing panelists before me. Thank you to the French Embassy in the UK and the York Festival for the invitation. Just as a disclaimer, I've left my original field of astronomy about 15 years ago. So while I've kept up with some of the developments in the field in space science out of interest, my main field of expertise is indeed now science diplomacy. So I'll have the bit of the unfortunate role of bringing us back down to earth after this amazing presentation. The lens I'd like to bring to this roundtable is a bit of the science diplomacy perspective, right? Where science diplomacy is a field where we try to understand the linkages between science and diplomacy. So, for example, how states deploy strategies and capacities to further their engagement around science and international realm, but also how science feeds into international policies, which ties into what Clement was talking about earlier. And indeed, science diplomacy is a field that started about 15 years ago and was framed in a bit of an overly positive way at the time, where it rested on the positive framing that science as a universal shared enterprise could serve as a bridge across political divides. And we've heard the example of the International Space Station, where despite tensions, scientists and astronauts have been building trust on parallel tracks. That premise hasn't disappeared, but I just want to bring about a little bit of the sort of changes that we've seen over the last decade or so, where we're living now what we're calling in the field of post-naive moment for science diplomacy, where we are increasingly in a more complicated position that we were, let's say, 10 to 15 years ago. We've seen the rise of emerging technologies that have been becoming more explicit tools for strategic competition, influence, and the object of restrictions and sanctions and so on. And we see also a multipolar world that is emerging with different geopolitical alliances, and that is also reflected in the ways that countries collaborate in various domains of science and technology. And all of this is actually very visible in the space domain. So I'd like to give you a few examples. I'll go with 3 or 4 examples, where some of them I've lived through, but I want to just start with the Earth observing part of the panel tonight, where often we, of course, look at the geopolitical context and the foreign policy issues, and we dismiss issues of national politics and of science policy. But these issues can have important repercussions in the international realm and our ability to actually solve global challenges together. And that again, I'm sure we'll address with Clement and Matt and others in the Q&A. But we've seen, for example, the hardening of the position of the Trump administration when it comes to in the US when it comes to climate science, for example, and the constant sort of push to defund climate science and also Earth observation satellites. While this isn't really been a defunding in effect, it has had led to uncertainty, threats of cancellation of mission, and issues on staff that have sort of led to damage that accumulates quietly, right? So that's a potential lesson for us to look at what has happened there, is happening, and also what could happen in the EU and potentially also in superpowers now in science like China, for example. So ESA has expanded its investments, but also increasingly framing this as European strategic sovereignty. For example, China has been ramping up its investments and is operating very large fleets of satellites. But so this, in a nutshell, is a bit of a representation of the fragmentation that we see now happening a little bit in scientific collaboration due to politics and sort of a multipolar world that we see emerging. I want to bring a quick case, again in the US, but that I lived through because I was a researcher at the time in the US in astronomy in 2011, and where the US, as a matter of foreign policy, decided that they would ban collaborations between NASA and the Chinese Space Agency, for example. And while it was later clarified that this was just on an official collaboration level, for a long time, this had repercussions on our ability as scientists to really collaborate with our Chinese counterparts, and could be for example, looking at whether we should hire postdocs and researchers from China, whether we should co-author papers with Chinese colleagues, and so on. And what I'm getting at here is that foreign policy issues and national, policy issues may have repercussions on the way that scientists are able to collaborate together to solve global challenges and to look at issues that are of blue sky science, issues that go beyond or should go beyond these geopolitical issues. Another case that is a bit closer to home, more recent in the European Union, is the follow-up of the Russian invasion of Ukraine, which has led to many freezes of collaborations between the EU, of course, and Russia. But you could see even there that the part of space exploration that we were talking about that should benefit all of us on Earth has stalled, right? For example, you saw a satellite, a German-Russian satellite called eRosita, which is an astronomy satellite, basically stopped, right? Because of these tensions and the invasion of Ukraine. And while the reaction is understandable on an emotional level, these kinds of decisions have had very serious consequences on our ability to continue blue sky science that really belongs to everyone. And then we've seen the rollout of blanket scientific sanctions as well from the EU that has repercussions on, let's say, our ability to monitor climate change in the Arctic, for example. My final case, to try to end on a more hopeful note, and thanks to the French embassy in the UK, I had the pleasure to be reunited with a classmate of mine. We did our PhD together, Dr. Kumiko Kotera, who's now the director of the Paris Institute of Astrophysics, and she's built this amazing French-Chinese neutrino detection project called GRAND, where they've installed many antennas in the Gobi Desert, and it's a thriving collaboration. And something that Dr. Patrick Nedelec knows well because he helped this initiative on the diplomatic side. And Kumiko said that science is one of the last frontiers of international diplomacy, and I think she's right, despite what I've said before. And I think the problem is that it's increasingly under strain, and the scientific community here needs to push back before it becomes really too fragmented, and before it is really fully at the mercy of geopolitical tensions and posturing. So just to wrap up, I think that while of course we can't be naive about all that's happening, I think we want to fight hard to maintain the areas of science that are critical for us to collaborate on, and we've heard many examples here. And quite a few of them, as you've heard, encompass issues that threaten humanity and our ability to live as a society right now, as we know, with all the systems that we have reliant on satellites and so on. But the issues such as climate change that are national security issues at their heart, and often governments see more of the immediate national security issues and not, let's say, climate change as a long-term national security or ongoing national security issue. Same goes for areas of blue sky science like astronomy. They not only advance our understanding of our place in the universe and contribute to a more peaceful, common feeling of togetherness, and have repercussions on things that we can do on Earth, as we heard Matt say, and Suzie as well. But they often also are a conduit for genuine and meaningful connections between countries, even rival ones. And hence, they also are an opportunity for discussions, informal discussions among scientists in turbulent times that can also serve a greater purpose of diplomatic engagement. So I'll leave it here and go back to Maria. I look forward to the discussion. Thank you.
Thanks a lot for that, the final talk of this session. We'll now move on to the Q&A session. I see that we already have some questions from the audience, and please feel free to post even more questions. I'll start first with a few questions for the whole panel. Well, first for Matt and Clement. So combining your fields of expertise, how can climate monitoring and space exploration work together to address the triple planetary crisis? For example, through repurposing technology that you already discussed a bit, through collaboration or research. Matt, maybe you want to start?
I can add, Clement, I don't know whether you wanted to come in on the Earth observation perspective first. You put your hand up. I'll let you go first.
Well, thank you very much, Matt. Your talk was really inspiring, and I think, only paraphrase what you were saying. Space exploration can definitely drive innovation that is useful on Earth. Technology developed for mission to the moon, Mars, and beyond often have environmental application, as you said. Can be advanced sensor, renewable energy technology, resource-efficient agriculture as well. And all those innovation can also improve sustainability and resilience on Earth while supporting future exploration mission. And of course, it supports international cooperation, which is always good. And we can also refer to the recent announcement for Artemis 3, bringing together all the world.
Completely agree, Clement. I think it's clear, at least for me, and maybe hopefully this comes across in our answers to this great question, that astronauts are already involved in tackling these sorts of challenges. So the astronauts regularly, while they're on the International Space Station, take many images to measure coral health and sort of marine biology cycles and that sort of thing. Of course, I mentioned what we call comparative planetology in my introduction. So what happened to Mars and how do we make sure that doesn't happen to us? Because we kind of like the fact that we have a bit of water on our planet. And yeah, I think there's a real opportunity to exploit some of the technologies that are developed through human space flight. So on the International Space Station, for example, the water recycling technology that we have, I think it is about 97% efficient. So They're reusing a lot of the water that they use to rehydrate their meals and to stay hydrated and that sort of thing. So making sure that we can use that technology back down here on Earth in perhaps areas where it's less prevalent. There isn't as much water around. How you filter and clean all of that water so that you can get a 97% return on your water is a great benefit for areas of the world that need it.
Thanks both of you. Yeah, some very good points there. I also recently saw actually water recycling system from the space station being repurposed for an Antarctic science station. So good example. So moving on to our two other topics. Suzie and JC, combining the topics of solar storms as a global risk and geopolitical fragmentation, if a larger Carrington level storm hit the Earth tomorrow or in 2 or 3 days, which was the time it took from the sun, would nations collaborate on recovery, or would it escalate tensions over limited resources? What's your feeling? What do you think? Who wants to start?
I don't know whether to jump in or not, actually. JC's the one who's an expert in the diplomacy rather than me. But I think, a massive Carrington size event impacts the globe. It doesn't just impact the area in which, the direct space weather impacts happen. It impacts everybody. It impacts our ability to travel. It impacts our power grids. It impacts us on such a fundamental level that it really truly is a global impact. And lots of reports have been published. People have been trying to estimate, what's the global impact on the economy? And, these numbers are not necessarily accurate. It depends a lot on the characteristics of the event, but the answer is probably some trillions of dollars. So pretty substantial impact. On the question of whether everyone collaborates with each other, in the forecasting community, yes. So we work very closely with colleagues in Europe, with colleagues in the US, to try to see if events are going to hit the Earth. And, this is done routinely. I'm sorry, my puppy is actually biting my hand as I'm talking to you, so just forgive me here if I get dragged off to the right. So we all collaborate really well on that. The response, I honestly don't know what would happen on the response front, and maybe JC has some ideas on this. Of course, I'm hopeful that space as an area of great collaboration could be extended further. If you think about things like we've talked about the International Space Station, what a great success that's been, but also all the space missions that we're involved in, they're all big collaborations. Collaboration in the face of disaster is much more challenging. And so I'm hopeful that we would all work together on our response, but I am less 100% positive, to be honest, than I would like to be. I don't know what JC thinks.
Yeah, no, Suzie, I think you said it, right? It depends in which communities, what part of the system, right? And yeah, I mean, we've had crisis, right, in the past, and we've seen that play out. Like we've seen the COVID crisis, for example, recently, right? And you see great collaboration with amazing, synergies between countries and so on. But you also see competition, right, on the back of that, and often also using the technologies developed for foreign policy gains and all these things. They happen, right? They're there. So yeah, I mean, now if we think about that big Carrington level storm, yeah, that would, that would be really bad. I think here for me, I don't think anybody has the answer really, but I think for me it will also rely on the strength of our institutions and the obligations that countries would have committed to also, right? And our preparedness in terms of, in that scenario, what is the right way to go? Even if, of course, again, competition, collaboration will always be there. Hopefully some kind of international obligations will be something that would be helpful to at least have a moral compass. And again, it's not exactly my field of study, but I know that there's been the Sendai framework, for example, that's been developed in terms of sharing data from space assets and sharing of space technologies and so on in terms of when disaster strikes. It's a bit of a different scenario, but we hope that might be helpful. There are UN institutions like UN Spider that have been also implemented to sort of recently, right, to look at these disaster effects. But I don't know whether such a massive event has been envisioned, right? I hope someone's thinking about it because, this is something that will open up dark corners around competition. So we need to mitigate this as much as possible through international legal obligations and governance structures that are really solid.
Thanks. Thanks both of you. And yeah, it's we sometimes, at least me personally, forget that we just been through this global crisis of COVID and pandemic because it feels like a parallel life somehow. But it's a good comparison. I think we will take one question now from the audience, and please still post your questions. Yeah, I see some more are coming in. We have a question here from David B, who is asking about any views the panel has on the economic impacts of the restrictions on collaboration and the nationalization of space science, which we are seeing. This JC, do you want to start?
Well,
maybe in this one.
Yeah, thanks, Maria. I mean, as I spoke just before, maybe what we could do is have the other panelists in sort of their sphere of domain, maybe talk a little bit about this because I'm sure they're seeing this, right? And then I can of course come in. But is that okay to do? Okay, great.
Perhaps I can start. I mean, the comparison will always be, if you want to go far, go together. I think that when you look at the European Space Agency, an international organization supported by many member states, it really is by coordinating the financial but also intellectual resources from all our member states that we are able to develop programs that which goes beyond what any single country in Europe could develop. So by not participating or contributing to such an activity, yes, you have a direct economic negative impact, and we can demonstrate for that many euros or pound invested at ESA, your economy will receive way more.
Yeah, if I might just jump in on the back of Clement's point, it's exactly the right stance, I think, is that especially in Europe with the European Space Agency, one of the kind of mandatory aspects, if you want to be a member of the European Space Agency, is to contribute to the space science program. So I think it's clear that when we all come together, at least as a European continent, we can recognize the importance of making sure that space science is done internationally and collaboratively. And where there are opportunities to do that with nations outside of Europe, then obviously we'll look to do it as well. But certainly within Europe, we have a strong tradition of collaboration on space science. And well, I guess, as I said earlier, space exploration can only be done internationally. Nobody's going to be able to do that sort of stuff on their own, for sure.
Thank you.
I guess I'll jump in just before we go to JC. Then I guess everyone's waiting there. The missions that I work on cost like €1 billion or something. No individual country is realistically going to be launching many of these €1 billion missions. It's just not possible. And so everything we do is collaborative. We work very closely with colleagues across Europe. We all have contributions in our own way. Maybe someone's contributing a big science research program. Other people are building instruments, but all of it is collaborative, and anything that stands in the way of that stands in the way of our scientific progress at the end of the day. And so, yeah, I think everyone on this call would probably agree. Yes. JC.
Yeah, no, thank you. So, I mean, I think in a way, I mean, when we think about economic impacts, you've said it, right? It's basically if you go at it alone, you're fronting all the economic cost, basically, right? You can, I mean, this is a very crude way of putting it, but if you collaborate, then it's a much easier sum of money. And I think, I mean, still very challenging for many nations, don't get me wrong. But I think this is the strength in terms of economic, gains to collaborate. Now, I think, it's interesting the framing on economic impacts, because I think, yes, there is an economic impact because of that, but there's a much bigger impact in terms of, the fragmentation and replication of all kinds of science that would happen. That really, while, friendly competition is fine and it's good to check results and do all kinds of things. At the end of the day, we don't want to operate in full silos, and then also deny access or restrict access to data that could be shared for the greater good, particularly when it comes to climate change or other observation issues and so on. And we see that rise, right, in terms of maybe the dual use issues and all these kinds of nasty issues that creep up. But it's really the effect on maybe our ability to use science for the global good. I think this is, for me, it's difficult to put it in economic cost, but it is there. So it's our global economic cost is what is hit, and so our own cost is there. Because, as Clement said, when we look at pollution, when we look at all this, transboundary issues, at some point, every of us has to clean up, has to mitigate, has to adapt, and all of this, and that's a huge economic burden. So anyway, just thought I'd put it in that framing as well.
Thanks. Thanks for these perspectives. And we have another question from the audience. A bit in the same direction. So when an important discovery is made in this kind of science, so we can again go field by field, who or which country owns the right to use it or to profit from it? I don't know who will want to start. Matthew, yeah.
Yeah, it was a toss-up between me and Suzie. I think that's from an academic point of view, but no, from a governmental point of view, this is part of the kind of reasoning behind why we would want to fund particular missions over others. So, for example, the UK is leading the charge on building the Rosalind Franklin Mars rover at the moment to go and answer, that fundamental philosophical question of, are we alone in the universe or not? But the way in which the kind of science outcomes will be delivered is that it entirely depends on which member state built the instrument on the rover that makes the discovery. So the UK are building a couple of instruments that are used to provide geological context, and they'll do a little bit of spectrometry to work out whether
I think we slightly lost the end of that, Matt, so I'm going to jump in and finish a sentence for you. So I think what Matt was saying was that lots of different instrument teams on Rosalind Franklin, for example, from different countries build different instruments, and they get the data back first, and that's a really great and amazing thing for that team, and they'll analyze that data. It is shared, and it has to be shared with the rest of the world. So it's not like we can get the data back and then hold on to it forever and get all the benefit. We can't do that, and we shouldn't do that. So the data is shared with everybody, but there'll be a little bit of time where we might get it back first. Now, if you take Rosalind Franklin as an example, or the mission I work on, Pepe Colombo's going to Mercury, there isn't really an economic impact we're going to get back from that. So I'm not going to invent something magical and make a billion euros for me and my group. I mean, maybe, but probably not. But there are other examples where there might be an economic impact and where we do need to think about where we invest our money for the best return. So I think it's quite variable across different science fields. I really hope I've just summarized, Matt, what you were about to say.
Excellent. Clement, do you want to come in on this?
Perhaps,
well?
I mean, I can only echo what Matt and Suzie were saying. And when it comes to monitoring our environment, understanding our climate, there is also a very strong financial impact. We talk about science, the great of goods, but of course, better understanding what's coming, the consequence of a changing climate, having more intense extreme events, it has a cost, particularly if you look at the insurance sector, for example. So it has definitely a cost. With benefits, I don't know, but it clearly has a very strong cost.
Yeah, another question from the audience, also a bit in the same direction, is how do you mediate the relationship between working together and competition in your field?
Can I maybe, Maria,
Yeah.
answer this, but linking to the previous question as well, maybe using an example from my original field in astronomy. So first, maybe just before I do that, I will say that sometimes here when we're answering, I guess we're not really addressing also commercial satellites as well, or private enterprise which also generates and they own the data and so on and make a profit out of it. But when it's public funded money, of course, it's like the nation is investing. They'll also want a return on investment on it. And there's what I think, Suzie, you were talking about is the proprietary sort of length of time where you benefit from the data, and then you can publish and be okay. The scientists can be publishing and so on, but then it's completely open to the world. I'm schematizing again, but it's in a way. Public money funds the scientists, and there's some return on investment from the country and so on for some period of time. I think, for example, in astronomy, we build very big telescopes, right, in the community, and we do often open a fraction of the observing time to countries and individuals beyond the consortium that has built the telescope, for example. So as a matter of access to ensure that the best science is being produced, there is a fraction of the time that is then accessible by everyone and the top scientists everywhere in the world. I don't know how it goes with maybe Clement can come in on ESA and Matt on other missions and so on. And so there is this sort of element of, investment and competition from a nation or a consortium. But at the same time, there's this, sort of window of hope that we still want to collaborate and do the best science that we can, right, with respect to the original investment that countries and so on are putting in at the beginning. So what I'm getting to is that there's this sort of constant back and forth between, investing and owning and using, and as well as ensuring that there's also the best science that is being done and accessed worldwide, right? So anyway, I just wanted to get that as well, get to that example.
No, absolutely, and here you touch upon a very important aspect of the new space and the commercial sector. Maria, you've mentioned at the beginning the Copernicus program. Here we have continuity in the data. If a private provider wants to stop and buy an island in the tropics, when it can happen. If a government tell a company to stop providing high resolution images in a particular place of the world affected by conflict, we don't want that. So that's why we build a program such as the Copernicus program to make data freely available to everyone all the time. And I think it's very important to keep in mind this sustainability and resilience of our activities.
So we have a couple of questions on space weather specifically. So one, and I will bundle them a bit together for you, Suzie. One I think you addressed a bit already in your talk, but is our society currently more or too vulnerable to space weather and space climate circumstances as we have branched out so much into space? And another one was if extreme space weather events are any cause for governments to deny climate change?
Okay, yeah, I'll take them in order then. So the first one is, are we very dependent on space? Are we more dependent on space? Are we too dependent? We are more. I think no one would disagree with that. Now we're using satellites as part of our everyday lives, even if we don't realize it, all of us are. And so our economies, our financial transactions, our navigation systems, we use it all the time. And we are quite dependent on it, for sure. Different areas of the globe may be more or less dependent on different systems, but in essence, yes. So as a result, of course, the impacts of space weather and other events, it doesn't have to be space weather, it could be space debris or similar, will have an increasing impact on us. And it's something that we need to be aware of. And I think people are beginning to be a bit more aware about the hazards of space exploration and space satellites and what we need to do about that. Is it a reason for people to be denying climate change? I think was the second comment I think people made. I think I can say categorically the answer is no. And so yes, Clement, phew. Yeah, so we do see these trends in the sun, right? And we do see cycles in solar activity. Of course we do. And I showed you a graph of that. That's very clear. And we see longer term changes too in the sun, changes that happen over hundreds of years, over thousands of years, and we know about these and we've looked at them in detail and we've analysed records of our climate over that time period as well. The most recent few decades specifically, but I guess over the last sort of century of changes in climate cannot be put down to any changes in the activity of the sun, I'm afraid. So we can't hope that the sun will just quieten down and solve all our problems, I'm afraid. These are made by us and they have to be fixed by us. But it's a really common question and kind of a good one, I guess, to clear up because, lots of people kind of have on their minds, maybe it could just be the sun that's different. And I'm afraid the answer is it's really our fault.
Thank you, Suzie.
Yeah. Good to have that cleared up, I guess. Okay, so we have one more question from the audience here. Where would you like to see the development in space Earth research head in the coming years? And is there any angle that is important for us to approach? And who would like to start with that? Clement, maybe?
Yes, I can give it a go. Thanks. It's a very, very good question. And at a time where we talk a lot about resilience, security, and the dual use of space, and very rightly so, don't get me wrong, we should not forget that short-range change of geopolitical strategy should not drive us completely away from the long-term need to better understand our climate, how our environment is changing. So we need to continue to develop a better activity towards understanding climate change. It can be adaptation, it can be mitigation, because perhaps that the battle against water scarcity or excess has already started.
Thank you. Matt, maybe you want to comment on this?
Yeah,
also?
if I can. Hopefully you can hear me okay.
Yes. We hear you now.
Perfect. I think my laptop's trying to do some kind of update at the same time. The fans have got really quite loud, so apologies in advance. I think one of the areas that I perhaps didn't lean on too much in my introduction is the drug discovery angle that we can do in microgravity. So in terms of information that we can learn about how the human body works, we can bring that down to Earth, and that helps sort of the elderly and the infirm. But then more interestingly, I think from a pharmaceutical point of view, the way in which crystals grow while you're in space allow you to sort of inspect the way in which proteins sort of shape themselves. And so effectively what you can do is work out what different types of structures of different molecules can even take, rather than what you can do in labs, you can only do it in the microgravity environment of space. And these different proteins can have all sorts of really useful benefits, like reducing side effects on really useful, important treatments, or increasing the power of insulin and sort of cancer treatments and that sort of thing. So there's a real opportunity for us to would potentially commercialize that aspect. So in the UK, at least one of our priorities recently announced by the minister is in-orbit servicing, assembly and manufacture, or ISAM for short. And the M in ISAM only exists, like we only know that it exists because of the research that's done on the International Space Station. So I guess from a space exploration point of view, I'd want to see, what is the next M in ISAM that we're going to establish for the benefit of humans down here on Earth.
That's very interesting research. JC, do you want to add something?
Yeah, I mean, I think I'll bring this sort of cynical that I've been bringing to the discussion a little bit, but not specifically on a technical level, right? I mean, there's many things that the experts here are saying should be done, right? But I think for me, it's more on the collaborative side in terms of ensuring that we can synergize all of us in terms of ensuring that we can tackle those global challenges, because really they are a national security threat, to put it in the sort of policymakers, sort of lingo, and to really ensure that we work together. Again, I maybe a bit of an idealist note here in the end, but I think that we need to act as a scientific community as a bit of a counterweight to the increasing tensions that we see in the geopolitical realm. And usually the scientific community is pretty good at being friendly and collaborative, right? And so I think that here we need to increasingly have discussions with our governments, the international institutions, and so on, together with all the scientific community, to ensure that restrictions on collaborations are minimized and that sanctions are not stifling science. Because again, the global challenges that we're facing are tremendous, right? So we just need to ensure that we fight that battle accordingly.
Yeah, thanks. Yeah, global challenges are global, indeed. I think this was the last question we would take from the audience. So, Suzie, do you have anything else to add also on this last question?
I guess I'll just keep it brief. I have a couple of things I just wanted to mention. I think some long-term vision is what I'd really like to see. So it's not really a practical thing, but a bit more long-term vision around what we want the future of space exploration to look like. So at the moment, we have a lot of short-term vision because we have a lot of government churn all over the world, and, short-term space strategies. Long-term space strategies are what we need. Where do we want to be 100 years from now, 50 years from now, and how do we get there? And what legislation do we need to put in place to try and ensure that space is collaborative, used for peaceful purposes, used for scientific purposes, that everyone benefits, and so on. So I think vision is one thing that I would really like to see kind of moving forwards, a bit of a longer term strategy. I'm going to stop there actually because I've got a friend to visit, so I guess it's a good moment to wrap up.
Yes, thank you, and thanks to the surprise guests here. So then I just want to thank all the speakers. You've been excellent. Thank you for your valuable input and points of view, the presentations and this discussion. And thanks also for all the questions from the audience. And that wraps up this session. And be sure to check out what else is taking place in this year's festival. And have a good evening. Thank you.